Okay, so for those who came in late, don't worry. I actually am recording my desktop in real time, so I'll be posting these on YouTube. So you can actually download the raw MP4 on the course website, or you can actually watch the video on YouTube. I'll be giving you a YouTube link after each lecture. Okay, so we're going to get into a little bit of math now, so we're going to start very slowly. This is probably not used a lot in industry, but it's a good introduction in order to ramp up to more advanced material. Okay, so the first supervised learning algorithm we're going to talk about is what's known as linear regression. Okay, linear in the sense that there's only one variable, x, or it's also called a univariate regression. And the goal is, given training example data, the goal is to find a first order line of best fit that fits through as many points as possible with the least amount of error, so that you can predict other things that you haven't seen before. All right, so create a prediction model by fitting a first order. So it's not quadratic, not cubic, it's first order line of best fit using example data, all right? So a good example would be the housing prices stuff that we talked about in the past. So a good example would be something like this. So, sorry, a little. Yeah, something like this. Here's a good example. So housing data, housing price data. Okay, so the goal is to find a first order line of best fit that'll fit through as many points as possible with the least amount of error. Okay, so predict house price, given the square footage. You seldomly use one feature in practice. You want to use as many features as possible to be discriminative, but we're going to do one feature for now, just as an introduction. We'll finally move to multiple features later. Okay? Footage. So something like this might work. So, maybe a line of best fit like that. It's a first order line, and then if you want to predict, the price of, let's say, $12.50, it might be something around 250 or so. So something like that. So that's a good example. So you create a prediction model that fits a first order line of best fit through as many points as possible with the least amount of error, and then use that to predict new instances. Okay, so let's see here. All right, so task is to create a model to predict, the palm rejection on this thing sucks, so to predict housing prices. Okay, so I'm going to start off with a little bit of notation before we get into some math. So here's some notation. Start out very slowly. Okay, so small case m, m as in Mary, will be used for the number of training examples you have in the particular problem you're looking at. Okay, so m, this is the number of training examples. All right. Okay. And then what we'll do next is I'm going to use small case x or superscript I with the bracket. So don't confuse this with exponentiation. So this is not x to the power I. This is the ith training example. Okay. So this is the ith training example. So this notation is actually used quite often, so don't confuse it with x to the power I. Okay, so this is not x to the power I, all right? This is the ith training example, and finally yi, this is the expected output given xi. Okay, so I will go from 1, 2, all the way up to as many training examples as you have. So x to the power 1, or x bracket 1 would be the first training example up to m. We have m training examples. Okay, so your table might look something like this. So let me see here. So you have, here's your training data. Well, it looks something like this. So you've got housing prices, or this is square footage. Okay, and this is price. So you've got something, it might look 2104 and then 1466. These are just random numbers that I just picked. So this is 460. This is in thousands, of course. Buying a house for $460 would be great, but that's unfortunately not the market right now. It would be awesome, but. Okay, so each of these is one training example. So this would be x to the 1, right? This is x to the 3. So this is the first training example, the third training example, and then the expected output. So this would be y1 and y3. Okay? So usually in supervised learning, you have pairs of x and y. So you have a feature or a value that belongs to your example data, and the expected output that belongs to each particular point. All right? So let's see here. So we usually represent each training example as a pair. So you usually see this in practice. So it's bracket, okay, where I is 1, 2, all the way up to as many training examples as you have. So you have tuples, or you have pairs of example points, right? So when you have more features, then you're going to have a vector of points, and then you have one training, one output at the end. But that's what's usually done. Okay, so let me just draw a nice diagram for you so we can talk about what the process is here. So if you recall the supervised learning model, okay, so first you've got some training data, all right? So this data is what is collected in the domain of the problem of interest. So if you're doing housing prices, you want to collect house information. If you're doing spam classification, you want to collect, emails. So you're collecting a bunch of training examples with the associated labels, all right? And then what you want to do is you want to create a prediction model. So create a prediction model with a learning algorithm, okay? So I probably should have drawn the circle a little bigger, but it's all right. Okay? And the output is a prediction model, which we'll call H. Okay? H stands for hypothesis. It's actually the vocabulary that was used 20 or 30 years ago, but it doesn't really apply now because hypothesis is an educated guess that you see in science, right? So the word kind of stuck, so people still use hypothesis as the prediction model, and you'll see that in a lot of machine learning textbooks, but the prediction model is also known as a hypothesis. All right, so this is known as a hypothesis. So if you see hypothesis or prediction model, they're pretty interchangeable. So training data, you create a prediction model, you get your hypothesis or your prediction model. All right? And then the goal after is you have a new instance or a new data point that you've never seen before or that wasn't part of your data set. So a new instance, right? So for example, in this case, it'd be size of the house in our particular problem. Okay, so here's a new instance. You're going to pipe it into the prediction model, and then the output will be the predicted value. Okay, so this is predicted value. Okay, so X will be coming in, and Y will be coming out. Okay, so that's pretty much supervised learning in a nice diagram. So you got your training data, create your prediction model, outputs a prediction model, put new stuff into it, and see what you get, see what the predicted value will be. All right? Okay. So let's see here. Did I get that right? Yeah. Good. Yes. Okay. So back to linear regression. So how would we actually represent this prediction model when you take a look at linear regression of fitting a first order line of best fit between as many points as you can? So let's see. Oh, there we go. Sorry. So how do we represent the prediction model for one variable linear regression, because we're only covering one variable or one feature for now. So actually, let me just go back up and let me just put a note here. So what we're doing is using only one feature. Forgot to mention that. So using one feature only. Just to warm up, all right? So just using one feature. Okay, sorry about that. Okay, so let's go back here. Okay, so let's default back to high school, right? So if you want to represent a line, what you need a slope and an intercept if you want a first order line, right? So we can represent our hypothesis or our prediction model as, okay, so here's your intercept term and your slope term. So theta 0 and theta 1. So what this is here, this is the prediction model or the hypothesis. Okay, and what this means here is it's parameterized by theta. So that means that you have a prediction model that is based on the slope and intercept that you found to fit the best line of, best line through those points. So parameterized by theta, which has two terms, theta 0 and theta 1. So this here is the intercept, right? It's also known as a bias term, because every single value in your prediction model will be offset by some bias or whatever the intercept term may be. All right, so this is the intercept term, and this here is the slope. All right, so the prediction model is a linear function. Obviously, there's only one variable, so this is a linear function, of course. That's the prediction model. Okay, so something, it may look like this. So just a quick example. So let's say you got a whole bunch of points here like that, Okay, and the goal is to fit a line of best points, right? So this will be represented as theta 0 plus theta 1x, okay? All right. We're going to start with a very simple linear model, and then we're going to ramp up our knowledge after this point. But the fundamentals that you learn from here will be a good basis to generalize to more, more advanced algorithms. Okay, so start with a simple linear model. Okay, as the foundation for more complex models. Later in the course. Okay, great. Okay, so we figured out how we're going to represent our prediction model. Now the next question is, what parameters or what theta 0 and theta 1 should I choose so that I can fit a line of best fit as best as I can through those points? And so the first question is, how do I represent the prediction model, which I just did. The next question is, how do I choose the right parameters to minimize the error and to make the, to make a good best fit of the data? Okay, so this is the next question. Okay, how do we choose the parameters theta 0 and theta 1 to best fit the points or the data? How do I figure that out? All right, so the idea, okay, is to choose theta 0 and theta 1 right? So we want to choose the right parameters where when you take each of your training example points and you put it through, this prediction model, it should be as close as possible to each of the output labels for each training example. So for example, if you had 10 training examples with expected outputs, you want to choose the right parameters where the difference between what is predicted from the prediction model and what is actually expected, the error is as small as possible. It kind of makes sense, right? It's the most intuitive thing you can do. So the idea is to choose theta 0 and theta 1 so that the prediction model, in our case this is h theta x, right? For each training example, so for I equals 1 to all the way up to m, is as close to the expected output right? It's as close to as possible. It's as close to the expected output as possible. Okay? All right, so how do we do that? Well, let's see here. Yeah, so choose this as small as possible. So how do we do this? So let me introduce, the linear regression cost function. Cost function is a buzzword that you probably hear. So linear regression cost function. Okay. It's also called an objective function if you specialize in optimization or anything dealing with that stuff. It's also called an objective function. So the idea is to choose parameters where every time you choose a set of parameters, it's going to cost you some amount in order to fit all those points to that particular line. So the higher the cost, the worse it will probably perform. So what you want to do is you want to choose parameters where it will give you the lowest possible cost possible, so that it will give you some, give you relatively good predictions. Okay, so cost, it's the cost function. So it's an objective function. So choose theta 0 and theta 1 that have the lowest cost. Okay. Okay, it's going to look like this. So usually cost functions or objective functions are represented by capital J, and then it's parameterized by two parameters, theta 0 and theta 1. And what it's going to look like first, well, you probably want to sum up all the differences, right? So from 1 up to m, sorry. So maybe you want to start off with this first. So this kind of makes sense to me. So what you want to do is you want to take a look at all your training examples and find the difference between the predicted value that's given by your prediction model, that's parameterized by theta 0 and theta 1, and you want to find the difference between the predicted value and the expected output. But usually what people do is the difference, it might give you a negative value. So when you're adding up all the costs, if you get a negative value, it's going to drive your costs down. So it will give you a false sense of security that this will be the right parameters you choose. So what people usually do is they square the cost function so that you're ensuring that there are no negatives when you're summing it up. All right? And then finally, what people do is they try to find the average error. So they usually divide by the number of training examples that you have. And then what people usually do is they usually divide everything by half. So they usually scale by a factor of 2. And the reason why they do this is because you'll take a look later, but if you, it just makes the math a little easier, and you'll see why there's a factor of 2 there later. So this is a lot to digest, but let's break it down. Okay, so this is the cost function. So this is the number of training examples, right? Okay, so this is the linear regression cost function. Okay, and then this is the predicted value of xi, so if going from 1 to all the way up to m, given theta 0 and theta 1, okay? And this is the expected value, yi. All right, so what you're doing is this is what's called the mean squared error. So you're taking the difference between the predicted and the expected, squaring them, adding every single one of them up, and then dividing by 1 over m, or multiplying by 1 over m, and then you scale by 2. Yes?
Sorry, wouldn't it be computationally cheaper to just find the absolute value of h?
The reason why the absolute value is because it's not what's known as a convex function. Because in order to guarantee a unique minimum, this function has to be differentiable. And if you have the absolute function, it is not differentiable. So that's why you square it, because it actually guarantees that this function is convex. So there's one unique minimum. If you have the absolute value, then it's not differentiable at certain points, and you can't use it when you're optimizing. So that's why I use the squared instead of the absolute. That's a good question, though. Okay? Does that make sense? Yeah. Okay. But I will cover that later. You're actually jumping ahead 2 slides, and that's good. I'm glad you're paying attention. But you have to square it in order to make it what's known as a convex function. If you do the absolute, even though it's computationally cheaper, it doesn't guarantee you a unique minimum. Okay? But that's a very good question. Thanks for asking. And I'll write that down later. Okay. Let's see. Okay, good. Where am I? Okay. Sorry, so let's see here. So you square the differences. I might as well just write it now because I just want to make sure we're on the same track. So you square the difference is to ensure no negative contributions. Okay, so the goal is to, let me see here, what is it? All right, so the best theta 0 and theta 1 to choose is the one that makes the cost function small, as small as possible. So you have, different combinations of theta 0 and theta 1, or, you can try different combinations, but the goal is to choose those two parameters that make this cost function as small as possible. All right, so minimize, j theta 0 and theta 1 for all. Okay, so what this is saying here is you want to minimize the cost function for all possible combinations of theta 0 and theta 1. So you got to figure out the right combination to choose. All right, so I'm just going to jump the gun here. So this is what is known as a convex function, convex cost function. Okay, so the reason why you square each term so that there is one unique minimum. So once you minimize this objective function, once you solve it, you will get a unique minimum every time. So there's no ambiguous parameters that will minimize, the cost function, which makes sense because there's only one best line of fit that will be able to minimize everything. You can't. There's not two lines, which wouldn't make any sense. So you square the terms because it's a convex cost function, which means that it's differentiable and you're able to minimize it. So there's one unique minimum. Okay, so it's also differentiable as well. Differentiable. So as I was asked on the floor, why do you not use the absolute value instead of squaring? It's because the absolute value will not make this function convex or differentiable, which would mean that there's not a unique minimum. Okay, so finding the absolute, and you'll see why later because the algorithm that we're going to use to minimize this is one that's known as gradient descent, which requires you taking derivatives. And if you have the absolute value, finding the derivative will be ambiguous because it's one derivative on one side will be one thing and then the other side will be another. So you have to be unambiguous when you're differentiating. Okay, so finding the absolute value would not make this convex. So that actually wasn't part of my notes, which is nice. I'm glad someone actually questioned it. Okay, so, okay. So you scale one, yep. Okay, all right, good. So this is known as the mean squared error, usually. So also known as the mean squared error, or the MSE. It's actually used in a lot of electronics and signal processing a lot, the mean squared error. So it's probably something that you're familiar with. Okay, so it's also known as the mean squared error, and it's used in many regression problems. Okay, so let me see here. Yep, that's good. One unique minimum. That's good. Good. Okay, so let's dive into the cost function a little more. I'm going to give you a little bit of intuition why we choose this. All right, so let's dive into the cost function a little more. So you'll see visually that the squared function is actually nice because there's only one unique minimum. Okay, so let's dive into the cost function a little more. Okay, so for now, let's assume that there's no intercept term. Let's set the theta 0 to be 0. So all you're doing is you're just fitting a line through the origin. Let's just make it simple and just assume that the intercept term is 0 for now. All right, so assume intercept or the bias term is 0. So we're going to set this to 0 for now. Okay, this will allow us to better visualize what's going on with the cost function. So I'm just going to assume that it is for now, just, but for the sake of, for not loss of generality. Okay, so this is to better visualize and get a better intuition of the cost function. Okay, there you go. Okay, so this corresponds to a line fitting through the origin. So there's no bias term, it's just a line that goes right through x is equal to 0. So corresponds to a line that passes through the origin. So it'll look something like this. So you got this, and then you've got a line of goes like this. So this is your hypothesis is just theta 1 of x. So there's no intercept term. Okay? So let's run just a small example. Let's say I've got a bunch of training data, and let's just start computing things. So let's see here. Let's show the hypothesis or the prediction model and the cost function side by side for different values. So let's assume for the moment we have 3 training examples. So let's say we got 3 training examples, and they happen to be, the following. So let's say we got this. So the first point is just 1, 1, the next point is 2, 2, and the last point is 3, 3. So let's say just by some magical chance that we get these these 3 points, which would be great in practice, but unfortunately it's seldom found. So, 1, 1, 2, 2, and 3, 3. Okay, let's say we got 3 training examples for now. All right? So what's going to look like is it's just going to be, actually, let me just make this a little better. Let me make the grid just the top right quadrant. So you got 1, 1, 2, 2, and 3, 3. All right? So 1, 2, 3, 1, 2, 3. And this is x, and this is h of theta. Not h of theta, sorry. It's just x and y. Okay? So, we have this line, and then what we want to do is you want to figure out the best theta 0 and theta, theta 1, not theta 0, that'll best fit this line. Okay? So, let's say I chose, let me see here. Let me just split this up like this. Okay? Oh, sorry. And let's say I chose, for example, let's say we chose, theta 1 to be 0.5, for example. All right? So in this case, you're going to have a line of 0.5x, so it's going to look like this. Okay? So this is, okay? And let's try computing the cost function. Okay? So, all right? Actually, theta. Oh, sorry, you know what? This is single variable, so let me just change this to theta 1. My bad. Because we're not considering theta 0 right now. Okay, so. Okay, if you remember, what was it? It was 1 over 2m, and then the summation between 1 and m of the prediction and the expected output. Okay, so let's just plug this in. So we know m is equal to 3, so you got 1 over 2 times 3. And then what's happening here? So this is theta 0, which is 0. So this is theta 1, x minus y. Okay, great. Okay, so I want to sum over all the training examples. So in this case, you got 1 over 6. And then this is what? 0.5. And then the first point was 1. And then you subtract it with the expected output, which is 1, right? Squared plus, and then what? You have 1 times, sorry. This is 2, let me see. Yeah, 0.5, 2. Okay, so remember this is theta 1x, right? And then finally we have 0.53 minus 3. Okay, so if you add this up, it's going to be 0.58. I'm pretty sure. Let me just double check. I think it is 0.58. Just run it down. Yes, 0.58. Good. All right. So what it's going to look like, let's say we plot this, okay? And let's say this is theta 1, right? So we've made sure that the intercept term is 0. On the y-axis is j, the cost function. So when you choose a theta of 0.5, the cost is going to be 0.58. All right? So it's going to look somewhere over here. Okay, so that's cool. So let's try another value. Instead of theta is 0.5, let's try, 1. So let's say we choose theta 1 equals 1. In that case, if you draw the line, we got 1, 2, 3. If you actually do take a look, this actually matches. So 1, 2, 3. If the slope is 1, well, obviously it makes sense because, the slope would be 1 in this case. So in that case, it just fitting a line of best fit through here. And you probably agree with me that the expected output and the predicted output are exactly the same. So if you actually calculated the mean squared error, you should get 0, right? So let's see here. So you get, let's see. All right, I'm sorry. So you get j of theta, right? Run through this again. One more time. Sorry, right, theta 1. Okay, so I won't bore you with the details, but it's just going to sum over and then it's going to be 0 every time, right? Because you're going to have, 1 times 1, right? Plus, and then 2 times 2, no, 2 times, we see 1 times 2. Sorry, can't get my math straight. And then 1 times 3 and so on, right? And that's 0. Okay, so in this case, what the cost function will look like is you have theta being here, and then this is the the cost, sorry, and then it goes here. Sorry, let me just get rid of that. Okay, so with one variable, what you do is you try different values of theta 1, right, to figure out which cost will be the smallest, so that that's the parameter that you choose. Okay, so we had 0.58 over here. No, sorry, this is 0.5. This is 0.58. Okay, so it's going to look like this. And then I'll just do one more just to be sure. Okay, I'll let you. I won't bore you with the computation. I'm just gonna. So let's choose some more. Let's choose a couple more. I'll let you verify this yourself, but you can see what I did. So there's 2 points here. So let's choose a couple more. So let's say if I make theta 1 equal to, let's see here, what did I choose? I chose 1.5. The cost that you'll get, if you want to verify that yourself, will also be 0.58. And then if I make the cost 0, right, this will be 2.33. Whoopsie. Okay. Again, bad polymer rejection. So the cost is going to look like this. Actually, let me just go here. Okay, and then, so here's the different, 1, 2, 3. Okay, so for each line of best fit that we have, for example, this one, it's going to map to a unique cost on the other side. So in this case, this was theta is equal to 1. In this case, at 1, you're going to get 0. Okay, and then you have a couple other ones. So for example, if I had, this is 0.5, it mapped to, 0.58, which is here. Okay, and then if I had just 0 like this, it's going to map to 2.33, which is right up here. Okay, and then finally 1.5 is going to look something like this. It's going to map somewhere over here. So you can see that it kind of looks like a quadratic function, which makes sense because that's what the sum of squares does. So it's going to look something like this. Actually, that's pretty bad. So again, that's bad too. 3 times the charm. Yay, okay. All right, so it's going to look something like that. So what you do is you want to figure out which parameter will give you the lowest cost. In this case, for our particular case, that'd be theta 1. All right, so the best, so right there, that's the best, that's the best cost. All right, so the best theta 1 to fit this example is the one with the lowest cost. Okay, So in this case, you want to find the theta 1 that minimizes this, right? In this case, it was 0, and theta 1 was equal to 1. Okay, in this particular case. So it was an artificial example. I just wanted to give you an idea of why the cost function is being used. All right? So in practice, we rarely get this kind of data. So it's very rare that you're going to get like a slope of 1. It's actually pretty, it's not impossible, but it's very rare. But if you do get that data, then that's great. But unfortunately, you don't see that in practice. Okay. All right. So in practice, you usually get data with a bunch of noise. So the goal is to find the parameters that minimize the amount of error that's seen between the examples and the predicted output. All right, so in practice, we rarely get data like this. Okay? There is usually noise. And we choose the parameters that give the smallest cost or the smallest error. With the training data, all right? So that was 1D. So let's actually go back to the original problem where there are two variables. You have the slope and the intercept. Okay? So in this case, the cost function is going to look like a 3D surface. You've got one axis, which is the theta 0, the other axis, which is the theta 1, and then you have the z, which represents the cost for each unique pair. So it's going to look like a 3D surface. And then with this cost function, you'll see that the surface kind of looks like a bowl-shaped curve. So there's one unique minimum that you will find given this bowl-shaped function. All right, so if you tried to do the absolute values, you wouldn't get that nice bowl shape, which is unfortunately, it's not differentiable and you can't really find a unique minimum. Okay, so back to, so there's light at the end of the tunnel. I'm going to talk about how we're going to find these, find these parameters in a second, or not a second, but in a little bit. Let's back to the original cost function. So now 3D. Okay, so theta 0 is usually the x-axis, and then theta 1 is the y-axis, and the cost is the z. Okay, so what this means is that this is the cost to choose theta 0 and theta 1 given the training data. Okay, so you usually get a 3D surface plot, so you can get it's now 3D, so you can look at it like this. So let me just find one for you. It's figure 9, I think. Ah, here we go. So it's going to look something like this. So this is a 3D surface plot, and how it works is you have unique pairs of theta 0 and theta 1. Each of these will map to a particular cost. So in this case, if I chose, theta 0 as minus 10 and theta 1 is 10, if I were to choose these parameters here, if I look at the height, maybe it's going to be around 10 or so. So this is saying that it's 10 given theta 0. This is just an example. It's nothing to do with the data that I'm currently working with. Okay, so something like this. Or if I were to choose, 0 and 10, it might be a little higher. I can't really tell, but so this case, it's going to maybe be 20, I guess. And theta 0 is 0, and theta 1 is minus 10. All right? So it's going to look like a 3D surface plot. So each unique pair of theta 0 and theta 1 will give you a cost, and that's on the z-axis. So the goal here is to figure out where the minimum of the surface would be so that it would give you the best parameters to fit your line, to fit your points. Okay? So each pair of theta 0 and theta 1 provide a cost for fitting the line, or fitting the points, not the line. Okay? So we got to figure that out. Okay, so we got to figure out where exactly it's, so the goal is to go find where the surface has the smallest height. Okay, so this is a little difficult to see. So what people normally do is they represent this with what's known as contour plots or contour figures. And what that is that it's basically a 2D projection of a 3D surface. So what a contour plot would be is if you take a look at this bowl shape, what you want to do is you want to take cross-sectional slices of this surface, and any points that belong to the same height, you pretty much project them on the 2D plane, and any points that belong to that same trace belong to the same height. So for better visualization, contour plots are used. These are actually pretty useful. Okay, so think of this as dividing your surface into cross-sectional slices. Dividing your surface into cross-sectional slices. Okay, so each slice has an amplitude, and you want to plot these slices, on the actual contour plot. So each slice has an amplitude, and you project on the XY plane. Okay, so let me just go back to the example. So let's say I had this thing again, which was this figure 9. Here we go. So let's say you had this, and then let's say you had like a cross section here. So let's say it was that, at I guess 10 or so, and it looks like this. You have a cross section like this, and when you do this, what's going to happen is you're trying to find points that intersect with this cross section. So maybe it might look something like this. Okay, and then when you have a contour plot, you have theta 0 and theta 1. What's going to happen is that it's going to look something like this. All right, and then all this have the same cost, so belongs to equals 10. So any points, theta 0 and theta 1, that belong to the same contour, so to speak, they share the same cost. So if I, went down a little further and maybe made another cross section this way, right, you might have something that goes like this, and this will map to that, and maybe this is 5 or so. So cost is 5. Something like that, okay? So let me just, instead of my botched, figure, this is what a proper contour plot looks like. So something like this. Oops, damn, try to drag it. Okay, good. All right, so let me just insert it again one more time, sorry. Here we go, so it looks like this, all right? So the contour plot might look like this. So for each trace, these belong to the same cost. So, points that are along here, all these points, belong to the same cost, or belong to the same cost. Okay? So this is color-coded. So blue would mean that it's at the smallest point, and then colors are increasing in terms of height. So the red would mean that it's the largest, and then the blue would mean that it's the smallest. So the minimum would probably be somewhere around here. So so this kind of makes sense. So you can think of each line as kind of like a thing that's coming at you. Each color corresponds to a height. So the red would mean that it's large, and then the blue would mean that it's kind of small. So each of these traces belongs to a cross-section of your surface. So this is a little easier to visualize. All right, let's see here. Okay, all right. So let me just include a couple more figures before we take a break. Just seeing how much time I got. Okay, good. So let's see here. So each color tells you all theta 0 and theta 1 values that have the same cost. Okay? All right. So here are the next couple of figures I'm going to show you. These are courtesy of Andrew Eng from Stanford. So let's say, for example, I have this pair. Okay, so I have these points, and then this corresponds to, okay, so if you take a look at, let's say I choose, theta as being 800, and then this is roughly about 0.12 or so. Okay, so this is minus 0.12. So this line corresponds to 800 minus 0.12 x, all right? So if I were to take a look at my contour plot and I chose these two parameters, this is the line of best fit that I get. And the cost is not that great, because if you take a look here, it's on the outer edge, and then this line of best fit is not good because it doesn't even follow the direction of the line. Okay, so that's what that would look like. And let me just show you a couple more. 12. Okay, let's say I chose something ridiculous like this. So in this case, the intercept is 0, right? Right, and let's see. Oh. It's a little weird. Yep. So there's no slope here, not the intercept, sorry. So in this case, the equation here would just be, this is roughly, I guess, around 375 or so, right? So this is just 375 plus 0x, so there's no slope. So obviously, there's, the cost is not that great either. It does fit some of them, but it doesn't even generally fit it doesn't even generally fit the points. Right, so if I chose, a couple of these, that's the line I would get. That's not really good either. Okay, and then here's another one. Just a couple more. Oops, that was the one I had before. Not good. Delete. Okay. Okay. Sorry, I chose the wrong one. 13. There we go. This is good. Okay. So I chose another one that's a little farther away. So this is 425, and then this is roughly 0.05 or so. So, okay. So that might be a little bit, it fits these points very, very well, but the extremities are pretty crappy. Okay, so the farther you go away from the minimum, which is definitely over here, the larger the cost is going to be. So finally, if you were to choose right over here, this is what the line would look like. Okay? And that's much better. So this is the point that corresponds to this line, and it's roughly 75 and then 0.12, I believe. Okay, so this here is roughly 75, and then this here is roughly 0.12. Well, positive 0.12, sorry. Plus. Okay, so this is, remember, this is the intercept term or the bias, and then this is the slope. Whoopsie. Damn palm rejection again. Okay, so slope. Okay, and that's pretty good. That's not bad. Okay, so what you have to do now is we have this surface, and what we want to do is take a look at the surface and figure out where along this surface the minimum would be. So there are different ways to do that, and the one that I'm going to teach you is what's known as gradient descent. Okay, so gradient descent is a technique that is used a lot in regression, especially classification 2, and it's a good technique to learn. So we know what we need to do. So we know what we need to do. So we have this surface, and we have to figure out where along this surface the minimum is going to be at, and that should probably give us the best parameters. All right. So let me just do this, and I'll take another break, and then I'll come back and I'll finish. Okay. So what we need to do to get the best. So we know now what we need to do to get the best line of fit. So the question is, how do we do it? Okay, and it's a technique which is called gradient descent. Okay, it's a technique that's used for minimizing objective functions. And it's used in many other areas of machine learning and pattern classification or what have you. Many areas of machine learning. Oopsie. okay? Not just regression. But classification too, and we're going to take a look at that later. Okay, so I'll give you a break now, and then when we come back, I'll finish this up, and I should be able to give you a little bit more insight on how we can find these best parameters. Okay, let's take a break.